Hey, good afternoon, everyone. Thanks so much for being here. My name is Will, and today Erik and I are going to tell you about our experiences taking some of the code we've developed with Spark for internal applications and making it consumable and accessible to other people by publishing it as a library. I'll start by telling you a little bit about myself. I've been at Red Hat for about a decade. I've done a few different things at my career, sometimes at the intersection of programming languages, distributed systems, and making sense of data, but almost always at the union of those things. And I've led a team of data scientists and engineers for the last 4 years, and currently I'm focused on putting AI into production in applications, internal-facing data science consulting, and contributing to upstream communities. So the two libraries that we're going to talk about today are the Silex and Isarn libraries. These are libraries we've developed. They're reusable open source code that we've mostly factored from internal applications. But we also sort of use these as sandboxes for new ideas. Like maybe we had an idea that we didn't think was fully baked and we didn't want to submit it as a PR to Spark. So we'd put it in one of these libraries. And we've been maintaining libraries that use or interact with Spark for quite a while now, over 3 years. And we've made a lot of mistakes along the way. So the main goal of this deep dive talk is to ensure that you don't make the same mistakes we did, right? Now, Erik and I were both experienced library developers in other environments. So we're going to cover some Spark-specific things that you'll run into when you're extending Spark with your own libraries. But you might be a really experienced Spark developer who's sort of new to developing libraries. So we're going to cover some more general issues as well, but looking at it from a sort of Spark-specific perspective of, this is sort of library concerns that you have working with Spark that you might not have elsewhere. Now, this is a deep dive talk. We're really thrilled to have the opportunity to give a deep dive. And we'll be structuring this talk in 2 halves. So I'll do the first session, Erik will do the second session, and we'll have time for questions at the end of each session, and we'll have a break in between. So we're going to go deep on a few interesting topics, and we're also going to call out places where you can go to learn more than we'll have time to cover even in this deep dive session after the session is over. With that out of the way, here's what we're going to be talking about. I'm going to start by introducing some basic considerations, some common themes that we're going to be talking about this afternoon for reusable Spark code, and look at how those considerations play out in how we test our code. I'll then talk about how to write generic functions for Spark's parallel collections, the RDD of the data frame, and also sort of introducing machine learning pipelines. And then I'll turn it over to Erik in the second half of the talk, who will introduce extending data frames with custom aggregate functions, which has a lot of sort of interesting things to worry about there, exposing libraries you've developed on the JVM to Python users, and then finally some considerations for publishing. And Erik is actually going to show you a screencast of us pushing a library release from earlier this afternoon, so you can see what our process looks like there as well. So let's start with these basic considerations. The most important philosophical point that I want everyone to keep in mind is that once you're a library developer, you can't control how your code is going to be used. You might have a great solution to correct someone's imperfect vision. And you might imagine one way that someone could use this. But once you release this solution out into the wild, it's out of your control. It might turn out that people are using your eyeglasses not just to wear on their heads and correct their vision, but also to focus the rays of the sun and start small fires. Similarly, when you're writing an internal function in your own program, you know how it's going to be called, right? Is the data frame that I'm operating on cached or not? You're in control. How many columns does it have? What are their names? What are their types? Am I going to be running this with a lot of partitions or a few partitions? What kind of executors am I running this function on? But once you write a library, all of that goes out the window. Anyone can use their code, your code, however they want, and probably in a way that you didn't expect. Another concern is doing things the right way. There are a lot of ad hoc solutions that can work when you're developing an application. It's okay to duct tape 2 things together and make them work. When we're developing a library that we want other people to use, these ad hoc solutions just won't do. We need to go the extra mile to use supported interfaces and play by the rules. This can mean a little more work for us as developers, but it will make life a lot easier for our users who will want to extend this code and use it in ways that we haven't anticipated. So a lot of the problems you'll run into as a library developer including with Spark, will fall into one of these two categories. Either challenges caused by users not using your code in the way that you expect them to, or challenges related to doing things the right way instead of relying on an ad hoc solution. And everything we're going to talk about today is going to reflect one or both of these themes. How many Scala users do we have in here? Okay, good. This is a larger percentage of Scala users than we have in a typical room anywhere in the world. I'm happy about that. So one aspect of not being able to predict how others will use your library is not knowing what environment it will run in, right? So for those of you who haven't done Scala development before, Scala minor releases aren't actually binary compatible with one another. So if you compile code for Scala 2.11, you'll have a library that you can run against Scala 2.11, but not against Scala 2.10 or Scala 2.12. So the way that the Scala community gets around this is you build multiple versions of your library. And this is something you can do as a library developer too. You can say, I'm going to use the cross-building facility in the simple build tool so that I can publish my library against multiple Scala versions. And this actually turns out to be pretty easy if you're using SBT to build. You just say, I have a default Scala version, but I also have a list of versions that I'm going to build against. And then when it's actually time to build my code, I can prepend, compile, or any other SBT task, like run tests, or package, or even publish multiple releases at once, to execute that command for every Scala version that I care about. So I can compile, test, or even publish multiple versions of my library with a single command. If I'm using this trick and I want to run a task just against a single Scala version, say a test is failing with Scala 2.11 but not anywhere else, I can do that too by prepending a double plus and the version that I care about to that task. So if you're a library developer and you only care about Spark 2.3, you actually get to escape this problem because Spark 2.3 is only compiled against Scala 2.11. So if someone's using your library and Scala on Spark 2.3, they're using Scala 2.11. But if you want to work against previous releases of Spark or future releases of Spark, this is going to be a problem for you because previous releases of Spark work with Scala 2.10 and Scala 2.11, and future releases of Spark will work with Scala 2.11 and 2.12. So if you've worked with SBT before, if you're one of the Scala fans in the room, you know that you can use this double % sign to automatically select the right version of a library for the Scala release that you're building against. Another thing you can do to sort of simplify making it easy for people to use your library in an environment you haven't anticipated is when you say, my library depends on these other libraries, you can say, I'm going to let someone bring their own version of Spark. Right? This means that you're not tied to the particular version of Spark you built against. This code will work against Spark 2.3, or it will work against 2.3.1, or a future version. And users can bring a Spark that's compiled by a distribution vendor, they can use an upstream binary, or they can even use one that they've compiled themselves. If we use this provided dependency scope, we can compile against one version, but let users bring their own. So that's a pretty simple thing that we need to think about to consider how people might be using our code in ways we haven't anticipated. But that's just sort of at the most basic packaging and building level. At the actual code level, though, we need to take these things into consideration as well. Imagine you have a model training algorithm that works pretty well when you run it once in a batch job. Probably built one of these before, right? But it might not run so well if you deploy it in an application that updates continuously. Maybe your code leaks some resource, or maybe it depends on some mutable state that it doesn't clean up after it runs. So running this more than once or running this many times causes it to crash. So to put this code in a library, you need to ensure that it works not just if you run it once, but also if you run it many times in ways that you haven't anticipated. Similarly, you might have code that works really well with a small number of partitions, but you've never tested it on collections with a relatively large number of partitions. Well, what could possibly happen to us when we change the partition count? It's probably still work, right? I mean, we would assume it would probably still work, but it's really easy to sort of accidentally have things that use linear time or space with the number of partitions. So you have an aggregate call instead of a tree aggregate call in your code somewhere. Maybe that'll work if you have a few dozen partitions, but not if you have a few hundred. Similarly, we need to think about how people are going to use the code in ways we haven't anticipated and test with large numbers of partitions as well as small numbers of partitions to make sure it still works. So as an example of leaking resources in a way that can cause problems for our users as a library, let's think about caching RDDs, right? If you're writing a function to operate on an RDD or a data frame, you want to ensure that it's cached before you make a few passes through it somewhere in the body of this function that we're not going to show because the body of the function isn't important, right? Now, caching indiscriminately is one of those things that you may be able to get away with at the Spark REPL or even in an application that runs as a batch job, but not in a library because we don't know how many times a client is going to call this, right? If the client calls this a whole bunch of times, eventually I'll have a whole bunch of RDDs that are cached, using up all of my memory. I won't be able to get any work done. And so we'll really want to unpersist this RDD when we're done with it. The problem is that if we're dealing with an arbitrary user-supplied collection, we don't know if the user wanted it to be cached, right? We don't know if the user gave us something that was already cached or not. If the user gives us something that's already cached, we don't want to uncache it at the end of the function because that's going to be surprising and irritating for the user who's going to expect that to still be in the cache. So what we'll need to do, instead of just blindly unpersisting this RDD at the end of this function, we'll need to do something else. We'll need to actually check to see if we need to cache the RDD. If the RDD was not cached at the beginning of the function, we'll test that by testing the storage level of the RDD. If it wasn't cached, we'll cache it. And then at the end of the function, if the RDD was uncached at the beginning of the function, that means that we cached it, so we'll uncache it. In this way, we're leaving the RDD as we found it, like a campsite. Right? We're not doing anything that's going to surprise the user, and we're still getting the benefits of caching there. In general, there are a lot of resources that you can potentially leak in Spark programs that you may or may not think about. Another example is broadcast variables. So here we have a skeleton of an iterative unsupervised learning algorithm. I've sort of blurred out the middle because, again, it doesn't really matter. We're going to start with an initial model, optimize it while processing the training set, and repeat that process for a certain number of epochs, which we have as the iteration count up in that for loop. Since our model is probably large, we're going to broadcast it so that it can be transferred to workers efficiently rather than serialized enclosures and passed around for every task. Now, if you only run this code once and you have a relatively small number of iterations, you can just create a broadcast variable at the beginning of every iteration and not worry about it, right? They'll go away when your program exits. But in general, this code might get called a lot of times. If it's in a library, it might get run with more iterations than you anticipate. You'll want to make sure that you clean up after those broadcast variables when you're done with them. So another resource that you have to worry about in applications where you can get arbitrary objects to operate on is the JVM heap. How many people have spent a lot of time thinking about how Java stores memory? How many people don't have to because they usually use data frames? Right. So this is something that data frames work around for us, but if you haven't thought about how the JVM stores memory, it's flexible but really inefficient, and it can come back to bite you in really surprising ways. So please don't actually represent a matrix like this in code, but this is a matrix, right? We have an array of arrays, and the fact that you can declare objects like this and operate on them is sort of both an advantage in terms of flexibility and a disadvantage in terms of overhead. And to see why, let's look at how this actually gets stored in the JVM heap. So we have an array containing pointers to two other arrays. So we have three objects. We have the enclosing array, we have the array for the first row or column, we have the array for the second row or column. We don't, not making any value judgments about row major or column major order today. And for each of those objects, we have a class pointer, we have some flags, we have a size field, we have space to store locks so that you can synchronize access to an object, and then you have the actual data, right? So we have a whole bunch of overhead before we get to the actual data, and in that enclosing array, the actual data is just pointers to two other arrays, right? So it turns out that in this array, if we have 8-byte double precision numbers, we have 32 bytes of data, but depending on how our JVM organizes memory, in many implementations, we're looking at 8 bytes per pointer and 16 bytes per object header, meaning that we're looking at 64 bytes of overhead. So like 2/3 of the space that this simple matrix takes up is overhead. And this isn't just a contrived example. If you look at the collection classes in the Java standard library, like the hash map is like 2/3 to 3/4 overhead if you have a hash map or a tree map, for example. So as a user, you know the advantages of data frames, right? They're a simpler interface. They have query planning and better performance in PySpark than RDDs do. As a library developer, another advantage of data frames is really important. And that's that data frames use off-heap memory so that they actually have an optimized representation of these kinds of structures that bypasses a lot of this overhead and improves performance. And you'll want to use data frames whenever possible as a library developer to avoid having this sort of JVM heap overhead. And it's OK to convert to RDDs in the course of developing your library, but you want to consider whether or not the flexibility of dealing with arbitrary objects is worth the extra memory cost, especially if it's something that you're going to have to keep around for a long time. There's another cool advantage of data frames and bypassing the JVM heap that's sort of related to how they make it easy to write generic code. We'll see that in a bit. But I want to talk about another surprising way that your code might be used in ways you don't expect first. And that's continuous integration. So a lot of people write tests before writing code, so we're going to put continuous integration relatively early in the session before we talk about a lot more to do with code. How many people use this as their Spark master when they're running tests locally? Yeah, I do, typically, right? Now, when you say that your Spark master is local star, you're saying I want one executor for each core on my machine, right? And what this winds up doing is it winds up taking the CPU and memory that you have in your computer and dividing it up. So that you have, if you have 16 cores, you have 16 executors. Now, those executors don't each get 1/16 of the memory that's available to your JVM because there's some fixed amount of overhead for each one of those executors, right? So you're not able to use all that memory, but it's OK if you have relatively a lot of memory for each of these executors. Now, what happens when we run this in hosted CI, like on Travis or a Jenkins installation somewhere? What's that running on? Well, it's running on a bunch of Linux containers where you have a very small amount of memory shared among a bunch of shares of processors. So it may look like you have 8 cores, but maybe instead of having 2 or 4 gigabytes of memory per core, you have 256 or 128 megabytes of memory per core. And so that overhead starts to look really, really bad when you have relatively less memory. A better thing to do is to say, I'm going to take all of that memory, that relatively small amount of memory I have in my containerized CI environment, and I'm going to spread it across a smaller number of executors and deal with it that way. Similarly, when you have code that if you sort of have a fixed large number of partitions, or you have a fixed large multiple of the default parallelism in your code, you're going to have a fixed overhead in your program for each of those partitions as well. And that may cause problems when you're running in a hosted CI environment that's relatively resource constrained. It's better, for the purposes of testing, to use a smaller number of partitions so that those overheads are going to affect the amount of data you do less. So now I want to talk about how we actually write generic code to work with Spark's parallel collections. And a really important aspect of developing libraries is making sure that your code is sufficiently generic, right? You want to make sure that it works on the widest range of data structures possible and in the widest range of situations. So the first of Spark's partition collections is the resilient distributed dataset. Anyone in here a big fan of RDDs? I'm a big fan of RDDs. That's a minority opinion these days. So we'll just spend a little bit of time talking about this because this is sort of a cool problem, especially for the Scala fans in the room. RDDs present a really interesting challenge for developing generic code. And the challenge is that RDDs are invariant, which means that if we have two types, T and U, so that T is a subtype of U, an RDD of T isn't a subtype of an RDD of U. If you're not used to talking about types and subtypes and variants and contravariants and invariants and all of these other things, concretely, what this means is that if you have a function that operates on an RDD of animals, you can't pass it an RDD of dogs, right? Even if a dog is a subtype of animal, which is sort of how I think of dogs as subtypes of animals. That they're a great animal, but they're still a subtype of animals, right? So as a concrete example, if we have some type that we've implemented as a Scala trait called hasUserID for things that have a user ID, we have some transaction class, and our transactions all have user IDs, we might want to write a function that operates on an RDD of anything that has a user ID. So anything that's a subtype of hasUserID. But we actually can't write it this way because we can't pass an RDD of transactions to this function that expects an RDD of hasUserIDs. In fact, if we pass this an RDD of transactions, this code actually won't compile. So there's a good way to work around this problem involving Scala's generic types and implicit resolution. And if you photograph this QR code, your phone may or may not take you to a blog post that actually explains it. And you can see the kind of detail we get into in the blog post over here. This is why we're not going to talk about it in the talk. So we're not going to have time to talk about the solution in this session because we'd really like to focus on data frames, which I assume more of you are interested in using than RDDs based on the show of hands earlier. So we'll look at an example of writing generic code that works on data frames. And this is a really simple example. This is natural join. The idea behind natural join is that you're going to take two data frames, you're going to identify the columns that they have in common, and you're going to join those data frames based on the columns that they have in common, and return a data frame with the union of those columns. Right? So we have one copy of each common column, and the way it's going to work is this. We have these two data frames. They have the columns A, B, and E in common, and we want to get the join of these where the values of A, B, and E are in common. So we'll select the ones that match, join them together, and then we have A, B, C, D, E, X, Y. So we could implement this in sort of an ad hoc way if we knew exactly the columns we were going to get, right? I could just write a query where I'm going to say df1.join df2 and where all of these columns have equal values. But in general, I don't know what columns I'm going to be operating on, right? I don't know what I'm going to be dealing with. I need to be able to deal with arbitrary data frames with arbitrary columns. So I can actually do it like this by introspecting over the structure of the data frames. And this is something important that you have to do as a library developer. So to identify the columns in common, I'll first look at the columns in the left data frame. I'll look at the columns in the right data frame. And I'll take the intersection of those to identify how I'm going to construct my join predicate. So again, we're introspecting over the names of columns here. Now, what I'm going to do next is dynamically construct a join expression. And all I'm doing here is combining together conditions for every pair of columns in the left and right data frame and creating their conjunction. So I'm dynamically creating an expression, again, where the left data frame for a given column has the same value as the right data frame for a given column. And then I'm taking the conjunction of that expression. So I have a list of expressions and I'm taking the conjunction of that. Does this make sense? So what this winds up looking like is looking like left.a equals right.a. I have a list of these things, and I'm going to turn that into the conjunction of those things. Right? And then finally, I'm just going to sort of filter down the list of columns that I care about by dynamically constructing a column list so that I only get each column once. Right? So this is a pretty simple example, but it shows you the power of introspecting over these things to be able to deal with arbitrary data that you haven't expected to see. And as you see, we even have a case for where the two data frames have no columns in common, right? We just sort of return an empty data frame in that case. All right. So if you're an experienced Scala user, you know that you can use Scala's implicit conversion mechanism to add this behavior to a regular data frame, right? So I have this natural join function. It's not part of the data frame class in Spark, but I can make it appear to be part of the data frame class in Spark. And the way I'm going to do this is have a special class that I call data frame with natural join that includes that natural join implementation I have. And then I'm going to have a way to convert from a data frame to one of these objects that just contains a data frame and has this special natural join method on it. And once I do that, if I import that implicit conversion object, implicit conversion function from that object into my other code, I can just use that nat join function on a data frame as if it had been declared in Spark's data frame class. So this is a really cool way to sort of add functionality to classes in Spark that you don't control. Of course, you aren't always writing functions that operate on entire data frames. Often you're writing functions that operate on a single row. User-defined functions are an important thing to have in libraries. In this case, we might want a function that takes out some subset of the fields of a structure and returns those. And this is pretty easy to do with data frame user-defined functions. We're going to assume we get a data frame of JSON. We're going to destructure it into a structure, and we're going to return a Spark SQL structure that just contains certain fields that we care about. Right, so I'm doing this example in Python. We can see we have the little Python logo in the corner of this slide instead of the little Scala logo that we have for the Scala-specific slides. And I'm going to sort of selectively destructure this by keeping only some of the fields. And basically all I'm doing here is I'm constructing a Python function that destructures something into JSON and returns the value for each of the fields that I get from the JSON object. And then I'm just going to return an empty structure if I run into an exception there. And then I'm just going to register that as a user-defined function with that structure type for the fields that I said I cared about. So for the example we looked at earlier where we had a data frame with people's names and card suits in it, we could just say we want to extract the fields B and X from the JSON objects in this data frame and add that as a new column. So the last thing I want to talk about before the break is Spark's machine learning pipelines, which are another really cool way to write generic functions against data frames. And we're not going to go in depth on machine learning pipelines today, but I just want to introduce the three key interfaces. Transformers take data frames as input and produce data frames as output. So this could be annotating a data frame with predictions from a model, or transforming values by scaling, encoding, or hashing them somehow. Estimators take data frames as input and produce transformers as output. So this, you can think of this as like model training or setting parameters for scaling. And once we have the model, that's also a transformer, so we can transform a data frame into one that has prediction annotations as well. So these three key interfaces are transformers that take data frames as input and produce data frames as output, estimators that take data frames as input and produce transformers as output, and parameters, which configure the execution of estimators and transformers, setting metadata like input and output columns, providing model hyperparameters, and more. Again, we won't have time to go into more detail about machine learning pipelines in this session, but if you scan this QR code here, it'll take you to a talk I gave at Spark Summit in San Francisco earlier this year about implementing scalable machine learning algorithms, and that covers machine learning pipelines along with some of these other considerations that are specific to scaling out machine learning. I'll encourage you to watch the video there if that's something that sounds interesting to you. We're at the halfway point of the talk now. And after the break, we're going to hear from Erik, who will show us how to implement user-defined aggregate functions, how to extend PySpark with code we've implemented in Scala, and some considerations for publishing our work, including a more or less live update to our Silex library. First, though, I think we have just a couple minutes for questions. If anyone has some so far? Yes? I can. I'll repeat your question, or you'll get a microphone.
Hi, thanks very much for your talk. As someone who writes libraries, a lot of the pains I feel are people who want to reuse my library, but then they always face exceptions because I can't find out how their environment is, and a lot of them are due to the fact that they're using different versions of different jars. So my recommendation is always, make an Uber jar so you've got all the dependencies you need. Is that actually the best solution?
That is a spectacular question. So, and this actually, I have some experience with this. I spent a lot of time working with the Fedora project, which is a Linux distribution, and it sort of has a philosophy that goes against the Uber jar thing. It's always like we're going to patch upstream so that they work with the latest version and we can ship one version of everything. That's way more work than making an Uber jar. But I mean, the problem with an Uber jar is that you're sort of exposed, you're hiding security vulnerabilities and performance problems that are in the classes that you bake into the Uber jar. It's definitely more convenient. So I think that's a trade-off, right? I don't know if that answers your question or not, but it's a difficult problem. I think that's definitely one of the better solutions for it, though, is just sort of encouraging people to go that way. Yes.
Is there a way to introspect data sets that have case classes as types in a similar way as you introspected data frames by getting back the column names?
So with data sets, you really you can lean more on the type system, right? There's the sort of limited introspection when you're dealing with a case class that you have in Scala in general, right? You can sort of treat it as a variant list, or it's trickier though. I think it's better to lean on the type system with data sets.